Okay, welcome to lecture here. We're going to continue on with chapter 8, which is gases. Uh, we're going to lecture for a little bit like we talked about last time, and then we will stop early, and then the quiz will open around 11. What is that? 11:30? No, not 11:30. Around 6:30 probably sounds a better time frame there. Um, then you can take it obviously at the last part there of lecture. And then if you have lab, obviously you could get off to lab and all that good stuff. All right. So we started talking about gases here in chapter 8. And remember, gases are obviously the state of matter where everything has pretty much broken apart from one another. They're flying around. As they're flying around, they are obviously colliding with one another. They're colliding with the container which they're in. That causes pressure that we associate with gases. Last time we sort of talked about some things that are sort of naturally found as gases, things like nitrogen, oxygen, hydrogen. Those are some diatomic guys, fluorine, chlorine as well, are diatomic gases. Our group 8 on the periodic table, which is our noble gases, are also obviously gases as well. We also talked about the idea that under normal conditions, we don't typically find ionic compounds as gases. Um, they typically will just sort of melt before they'll kind of go into the gas phase. And that's a little bit different than sort of molecular compounds. Molecular compounds will typically be maybe not a gas under normal conditions. But the difference between sort of a molecular compound and ionic compound is in a molecular compound, you could kind of convert it into the gas state a lot easier. So water is a very good example of that. We know water normally comes in sort of the liquid state very easily just by boiling pretty much water. You can convert it into the gas state. And that brings up a good sort of difference between two words that are sometimes used sort of together or maybe sometimes as sort of the same meaning. And there is actually a sort of difference between when we refer to something as being a gas or we refer to something as being a vapor. And the difference is if something is a gas, then it is normally under normal conditions of sort of temperatures and pressures, it is normally found in the gas state. Now, something that is under normal sort of temperatures and pressure found in the solid state or the liquid state that does get converted into a gas is an example of what we sometimes refer to as a vapor. And water is an example of that. We oftentimes talk about water in the gas state, which is this. We oftentimes refer to this as water vapor. And that's again because water is not normally found in the gas state, but it can sort of relatively easily be converted into a gas in that particular case. So again, there is sort of a difference when you refer to either a vapor or a gas in terms of sort of the meaning of those two things. Any questions on that there? So let's talk a little bit about gas and some important properties of gases. And one really important property of gases is obviously pressure. And again, as I mentioned just a second ago, as those gas molecules are basically flying around, they're going to have a lot of collisions. And these collisions, a lot of times with the container they're in, basically will cause the pressure that we associate it with gases. A barometer is a instrument that is used basically to measure atmospheric pressure. We'll see a much prettier picture of it in just a second, but basically, traditional barometers basically a pool of mercury. Inside that mercury basically is a glass tube. And as the atmosphere sort of applies pressure to the mercury, mercury kind of rises there in the tube. And that's basically where we can sort of take our reading. Mercury is an unusual liquid. It actually will make like a inverse meniscus. Actually goes up on top as opposed to traditional meniscus, which is like water sort of goes the other way around. They've taken a lot of those out of labs because, well, it's mercury. So they've taken a lot of those sort of barometers out of labs. Now I have more of a sort of a dye or alcohol sort of based barometer, kind of a similar sort of concept. Three really important units for pressure. One is an ATM. And again, don't get any money out of that. That is an atmosphere. Other two common units of pressure are torr, named after the gentleman there that discovered the barometer, and mmHg. And mmHg is millimeters of mercury. Why is it millimeters of mercury? Well, that little glass tube that was sitting in a barometer pretty much has a ruler on it. And basically, sometimes those measurements are in millimeters, like on a ruler. Sometimes they're in centimeters, sometimes they're in inches. And that's what it means. Basically, you're kind of measuring it like a ruler, millimeters of mercury. The relationship between a millimeter of mercury and a torr is a 1-to-1 relationship, and 1 atmosphere is 760 millimeters of mercury, or 760 torr. That 760 is an important number. It is like a conversion factor. So if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760. And again, that would give you millimeters of mercury. And that is basically the same thing as a torr. And vice versa, if you started with millimeters of mercury or a torr, you would actually divide by that 760. And again, those guys would cancel out your millimeters of mercury or torr, which again are the same thing, and you would get an atmosphere. So that little conversion, that number of 760, an important sort of number here as we do sort of conversions. Any questions on that there? Here's a much prettier picture of a barometer, like I promised there. And again, essentially what's happening is a traditional barometer does have that sort of pool of mercury. The columns also fill with some mercury. And again, as sort of the atmospheric pressure pushes down on that mercury, kind of rises there in the column. And again, as you can see in this picture, the meniscus on mercury, unusual sort of property because it's mercury, actually is an upward sort of circle. And you would read it. And again, like I said, on most barometers like this, there's like a ruler kind of here. And you basically read it just like you would a ruler. Hence why, again, it's sort of a millimeter of mercury in terms of its units. So we're going to talk about some different gas laws. And when we talk about gas laws here, there's really sort of 3 variables that we deal with in sort of gases. One is P, which is pressure. One is V, which is volume. And one is T, which is temperature. And we're going to see a number of different gas laws here in this chapter. And a lot of times we may keep one of these sort of constant and deal with the other 2. And sometimes we may actually deal with all of them together, and we'll see sort of an equation like that. So these are 3 sort of common sort of values that we deal with sort of in gas laws. So let's take a look at really the first sort of gas law that we're going to talk about, and this is what is known as Boyle's law. And Boyle basically studied the relationship between pressure and volume, and he held temperature constant. And basically what he found was at constant temperature, the relationship was the pressure would increase as the volume decreased. So if you just think about it sort of logically, if we have gas molecules flying around and we basically drop the volume of them, and they're now in a much smaller area flying around, there's going to be a lot more collisions happening. Because they frankly have no room to fly around. So as they're moving around, they're going to be hitting each other, hitting the container a lot more often. All those things are going to lead to a much higher pressure happening in that situation. Opposite of that would be he saw that the pressure went down as the volume went up. And it's sort of the opposite relationship. And what we mean by that is essentially if I increase the volume, it's going to give everybody a lot more room to fly around the gas molecules. It's going to take longer for those collisions to occur. Because it takes longer for those collisions to occur, we're going to actually have less collisions happening. And what will end up happening is we will see the pressure start to come basically back down. So that's what's meant by an inverse relationship between pressure and volume. Basically, as one goes up, the other goes down. So a relationship that develops from what's known as Boyle's law is this equation down here. This formula down here is basically Boyle's law. You do need to know, obviously, any of these guys in boxes. And this is pressure times volume equals pressure times volume, sort of a, if you will, a before and after type situation. And basically what would happen in this situation is one of these things would change. The other ones would kind of stay the same. And we kind of can figure out what happens in that deal. Now, in terms of units, pressure here could be pretty much any unit you want, as long as they are the same on both sides, so everything cancels out correctly. Volume can also be any unit you want, as long, again, as they are the same on both sides. If they are not the same on both sides, then you do need to do a conversion. But if they are the same on both sides, then you're good to go. In terms of that, you don't have to do any type of conversions. So Boyle's law, pressure volume relationship at constant temperature, as one goes up, the other goes down, is basically the relationship that we see. That's also what we see when we look at a Boyle's law graph, which is basically what this is. This is a Boyle's law graph, and we do see exactly what we were just talking about. We see that at small volumes, down this way, high pressures, and we see at larger volumes, lower pressures. Again, giving everybody a little bit more room to sort of move around. Any questions on Boyle's law? All right, so why don't you give one a go here, see what you come up with, and we'll talk about it here in a minute. A balloon is inflated to 0.55 liters at 1 atmosphere. It goes to 6.5 kilometers, where the pressure is 0.4. Assuming that the temperature remains constant, what would we expect the final volume of the balloon to be? So take a moment or two and see what you come up with. To sort of take the information out of the problem, and that oftentimes will help you sort of figure out maybe what gas law to choose from. Obviously, in this case, we've only talked about one, so that's probably the right choice. But if we go through this, we got a volume that is 0.55 liters. It's at sea level at 1 atmosphere. Again, remembering that an atmosphere is a unit of pressure. So we have a pressure. Gives rise to 6.5 kilometers, which is really useless information there. Where the pressure is 0.4 atmospheres. So that would be another pressure here. And we're looking for a volume. So again, by just sort of labeling these things, you know, it should be very apparent that Boyle's law is probably the right one here to use. And again, that is our P1 V1 equals P2 V2. In terms of the pressure here, we have the same unit on both sides, so we don't have to do any type of conversions. We don't have to do anything with our volume either. It just means when we're all said and done, our volume will be in liters. So one thing as well, you know, kind of sometimes this one might not be that difficult for some people, but rearranging some of these gas laws give people trouble. So even though these really aren't fractions, you could kind of think of them as like fractions over 1. And basically, when we go across an equal sign, and we were trying to sort of move something to the other side, they always end up in the opposite location. So in this particular case, we could label these guys as 1s. We could label these guys as 2s, which means I want to solve for 2. That means I need to bring my P2 to the opposite location, which would be on the bottom on the left-hand side. And that will give me the rearranging of this equation sort of correctly here. So as you move across the equal sign, everybody ends up in the opposite location. If they were on top, they end up on the bottom. If they're on the bottom, they end up on top. That's just sort of a quick way to sort of move things around. Now, the other important thing is we obviously want to make sure that we do put these things in the right spots. So that's going to be 1 atmosphere times our 0.55 liters divided by our P2, which is 0.4 atmospheres. Our atmospheres on top and our atmospheres on the bottom will cancel each other, and we will be left with 1 times 0.55 divided by 0.4 ends up with 1.375 as the answer on the calculator. Those units that would be left is liters. And really, because everything is 2 significant figures, 1.4 liters is really what we should get here at the end. Any questions on that there? Now, understanding the calculation and understanding what is happening in Boyle's law, it's important to help you know if you really kind of messed up on your calculation. So what did we see here? If we look at the pressure, it went from 1 atmosphere to 0.4 atmospheres. So the pressure went down, which means we would expect the volume to go up. And we could see if it did. It started at 0.55 liters, ended at 1.4 liters. So because we understand, hopefully, the inverse relationship of what's happening with the volume and the pressure, we do see that our answer does make sense. Any questions on that? Okay, so that is Boyle's law. We're now going to talk about another gas law, which is our good friend Charles' law here. So Boyle dealt with pressure and volume and kept temperature constant. Charles' law dealt with volume and temperature and kept pressure constant. And that gave us a Charles' law relationship of what we see down here, which is V1 over T1 equals V2 over T2. There's also another sort of relationship that's very similar to this one that we oftentimes will see as well, and that is what is sometimes referred to as Guy-Lussac's law. And that is where he looked at pressure and temperature and kept volume constant. And what is that sort of gas law? It's pretty much the identical one, except that it is P1 over T1 equals P2 over T2. So let's talk about these two gas laws and sort of what is happening here in each of them. First off, the pressures on each of them are on this one here. It could be any pressure you want, any unit, again, as long as they are the same. The volume down here for Charles' law can be any unit you like, as long as they are the same. Temperature in these gas laws and pretty much every single gas law you come across do need to be in Kelvin. So it is a safe bet that if you are doing a gas law and you have temperature, you best convert it to Kelvin. Even in a problem where they may give you the temperature in some other unit and they may ask you to solve for the temperature in some other unit, when you put it into the gas law, it has to be in Kelvin. So you got to convert it out of that unit to Kelvin and then convert it back to the other unit. So sometimes very common, you'll come across some problems like that where they kind of give you temperatures in like Celsius and they're like, what is the temperature in Celsius? So a lot of times people will think, well, they gave it to me in Celsius, I need to give the answer in Celsius. It would make sense just to leave it in Celsius and put it in the gas law, but you actually do need to convert it to Kelvin first and then kind of unconvert it afterwards into the unit that you want. So what are these sort of relationships that are happening in each of these? Well, let's talk about sort of over here, Guy-Lussac's law first. So this is a situation where we're at constant volume, which means here is my volume right here. My volume is not moving. Because my volume is not moving and I got gas molecules flying around, if I increase the temperature, for example, those gas molecules are now going to be flying around a lot faster. And because the volume is not going anywhere, we are going to see an increase in collisions. And because we would see an increase in collisions, we would also see an increase in pressure. And again, because we have a fixed volume in that case, as they're flying around, nothing's moving to give them more room. There's just going to be an incredible amount of increase in the amount of collisions, resulting in higher pressure. What would happen if we sort of lowered the temperature in this situation? Well, if we lower the temperature, our gas molecules are going to be flying around a lot slower. So instead of flying around crazily in that container, they're going to be moving a lot slower. And it's going to take longer for those collisions to sort of occur as they're slowly making their way around the sort of flask or whatever they're in. And we're going to see an actual decrease in pressure. So because of this constant volume, what's going to happen is they're pretty much one-to-one relationship there. If you increase the temperature, you would expect the pressure to increase as well. And if you decrease the temperature, you would expect the pressure to also decrease as well. Any question on that relationship there and that guy? Now, what about Charles' law and that relationship? Well, in Charles' law, we have sort of a different situation occurring. The only thing that's constant is the pressure, and we want to keep the pressure constant. So what that means is the volume can move. So in this particular case, what would happen if you had your gas molecules and you decided to increase the temperature? Because those gas molecules are going to start flying around faster, we would expect this situation to occur. But because we want to keep it at constant pressure, what it's going to do is actually increase the volume. So by it increasing the volume in the container, it's able to keep the pressure constant. So unlike in sort of Guy-Lussac's situation where the volume doesn't move, here the volume moves, and that moving of the volume allows the collisions to maintain sort of the same rate, and we are able to maintain basically the same sort of pressure as constant pressure. Opposite occurs here. If we decrease the temperature, just like we talked about here, everybody would be flying around slower. But what's going to happen in that case is if you decrease the temperature, the volume will also decrease. And now that the volume kind of came down, that's going to allow these gas molecules to basically keep the collisions happening at about the same rate. And we will see that the volume will basically decrease as well. So Charles' law is basically, again, as one goes up, the other goes up. And as one goes down, the other goes down as well. Any questions on those relationships there? Okay. So why do we have to sort of put everything in Kelvin when we do gas laws? It's really because if you take a plot of any gas you like, you can choose any gas you like, and you plot volume versus temperature, and you basically extend each of those lines backwards to the temperature axis. They all hit the exact same spot. They all hit a temperature known as 273.15, I'm sorry, minus 273.15 degrees Celsius. You might remember that number because if I want to convert Celsius into Kelvin, I would add 273.15 to it. And that gives us 0 Kelvin, which is known as absolute zero. And it's actually Kelvin who basically recognized this behavior And basically, again, in any gas law that you use, that temperature needs to be in Kelvin. And again, that is basically 273 plus the temperature in Celsius. You don't have to use the 0.15 unless you really want to. Any questions on that one there? All right, so why don't you give one a go here and see how you do. In an experiment, we have 452 milliliters of a gas in a light bulb, goes from 22 to 187 degrees Celsius. What is the final volume? So take a moment or two here and see what you come up with. Okay, so let's take a look at this one. And again, as I mentioned in the previous one, you do want to kind of pull out the information. It just makes, maybe picking the right formula a lot easier. So obviously we have 452 milliliters. We have a temperature that's 22 degrees Celsius. We have another temperature that's 187. And we are looking for a volume here. So just by kind of looking at these guys, kind of labeling these guys, Charles' law really should sort of jump out at you. Obviously, Boyle's law would not work since there's no pressures. Guy-Lussac's law would also not work because there's no pressures involved. So again, that's why it's sometimes important just to pull out the information, kind of label everything, and you're able to see it. We do see temperature. And again, one thing that we just talked about by temperature is we need to make sure that we convert it to Kelvin. So we're going to add a 273 to the 22. That gives us 295 Kelvin. We're going to add 273 to our 187, and that gets us 460 Kelvin. In this case as well, we can see that we essentially are going to be solving for V2, which means we want to get V2 all by itself. That means that essentially we need to move the T2 to the other side. Again, this is where sort of opposites come into play, and it makes it a little bit easier perhaps. He's going to end up on top since he started at the bottom. That would get us V1 T2 divided by T1 is equal to V2 in this case. Now that we have everybody in the right units, again, volume could be any unit you want, but in this case, it will be milliliters at the end. We also want to make sure that we put the numbers in the right spot. So 452 milliliters up on top, T2 up on top, which again, very common. Sometimes people get the temperatures backwards. And we want to divide by 295 Kelvin. The Kelvin on top and the Kelvin on the bottom will cancel. That leaves us milliliters there up on top. That's a 452 times a 460 divided by a 295. That is going to get us, I believe, what I saw in the chat box there, which is good, 705 units. Again, going to be milliliters because that is the only one that is left at this point. Any questions on that there? Again, understanding the relationship of Charles' law that as the volume goes up, so does the temperature. And as the volume goes down, so does the temperature. We could see if our answer makes sense. Here, the temperature went up, which means we would expect the volume to go up, and it went up from 452 to 705. So again, it does make sense in terms of, what we got. Question on Charles' law, Guy-Lussac's law, any of those guys there. Now, there is one more sort of law before we get to the next one, which is basically the ideal gas law, and basically putting together Boyle's law, Charles' law. There's also our good friend, we can't forget, Avogadros' law. We'll throw it in there just for fun, just to make sure. Avogadros' law is V1 over N1 equals V2 over N2. Avogadro had a number. He wanted a gas law too. All right, so Avogadros' law here. And this is actually at constant temperature and pressure. And V is volume, just like we've used before in this last couple. It could be any unit you like as long as they're the same. N is actually moles. So N here is moles. And sort of taking Avogadros law with Charles' law that we just saw and Boyle's law and kind of putting them all together, we get really sort of the granddaddy of them all in terms of gas law. And this is what is referred to as the ideal gas law. The ideal gas law is PV is equal to nRT. You will also notice that this equation here is different than the ones that we've seen previously. And that is because there is no before and after. So what I mean by that is there's no two pressures, there's no two volumes, there's no two temperatures. This is pretty much a one and done type situation. And so that's a very major difference in terms of sort of the ideal gas law versus others. Other really important things about it is units. When you use the ideal gas law, the pressure has to be in units of atmospheres. No other unit will do. Volume, the units has to be in liters. No other unit will work correctly. N should be moles, as I just talked about. T, just like everything else, needs to be in Kelvin. So in addition to being sort of like a one situation and done type deal, it's also the most restricted in terms of units. They absolutely have to be in these units. Why do they have to be in these units? They have to be in these units because of R. R is the gas constant, and it has a value of 0.08206. Some people will round that number to 0.0821. You can use any number you like. I personally use the top one because that's what they beat in my head, so I can't get it out. But more importantly, the units that are associated with this is liters times atmosphere on top, Kelvin times mole on the bottom. So this gas constant, which is a constant value, so you always have R. So that's something to remember as well. You always have this number, and it has all those units. The other nice thing is if you can't remember the units you're supposed to use over here in the ideal gas law, and you look at the R value that probably will be given to you, it tells you what every single unit pretty much needs to be in when you're using the ideal gas law. Question on that there. What is an ideal gas? An ideal gas is essentially a gas that we deal with in this class and in most classes. And a couple of things that make something an ideal gas is the idea that we assume that the gas itself has no volume, and we just look at the volume compared to the container it's flying around in, and there's no attractive forces between one gas molecule and another. So that's sort of what makes something an ideal gas, is even though it may be flying around in a container with a whole bunch of other gases, we assume sort of ideal conditions, that it's not really interacting with anybody in there and is not going to have any interaction with any other gas molecules that are flying around. And we also assume that its volume is relatively small compared to the volume of the container. So the ideal gas law is sort of a really important one. Again, it's used in sort of a one situation type of deal. Another couple of important things in terms of the ideal gas law that we see on sort of this slide here is there is a relationship that is known as STP. And what STP stands for is actually standard temperature and pressure. So when somebody says we're doing this at STP, they're actually giving you a temperature, and that temperature is 273 Kelvin, even though they don't straight come out and tell you it's 273 Kelvin. And they are giving you a pressure, which is 1 atmosphere. So when they say in a problem, do this at STP, or this experiment was done at STP, those are the two values that you could use for temperature, 273 Kelvin, and pressure, 1 atmosphere. Now, there's actually a relationship that occurs only at STP conditions, and that is 1 mole of any gas that you have will equal 22.414 liters. You could actually use this conversion, again, only at STP, to actually not even have to use the ideal gas law. So you can actually use this, sort of go around the ideal gas law, but again, you can only use it at STP conditions. You could use the ideal gas law at every condition, including STP conditions, you could just put the numbers in, 273 in 1 atmosphere. So if you can't remember this, guys, not all lost. You would still use the ideal gas law. You would just put these values in for pressure and temperature. Question on that. That is actually where the value of the gas constant comes from. If we take the ideal gas law and solve for R and put in the values at standard temperature and pressure conditions, which means we have 1 atmosphere, we have a volume of 22.4, we have 1 mole and 273. That is basically where we get our ideal our gas law constant there of 0.08206, basically. Any questions on that particular one there? Okay, so let's take a look at one here and just kind of see how it is different than maybe some of the problems that we saw before. We want to calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a steel vessel at 5.43 liters and 69.5 degrees Celsius. So if we were going to approach this, we would want to pull out the information just like we did before. We're looking for a pressure. We have moles, that is 1.82. We have a volume that is 5.43 liters. We have a temperature that's 69.5 degrees Celsius. So just by pulling out the information, we see we don't have 2 volumes, we don't have 2 pressures, no 2 temperatures. Kind of can see the ideal gas law there. So again, it's a very good approach in these problems to do that. It should point you in this direction here of the ideal gas law. You could even check off what the things you're looking for. So you got pressure, you got volume, you have moles, you have temperature, you always have R. So again, because R is a constant, that is a value you always have available to you. Again, they may not tell you in the problem what R is, but it is always there for you. So really at this point, we want to just check units. Moles are good, liters are good, but our temperature is not good. So remember, we do need to get that into Kelvin. So we would want to convert that into Kelvin by adding 273 to it. And if we do that, we end up with 69.5 plus 273. Gets us 342.5 Kelvin. And now we have everything that we need. So we could take our PV equals nRT. We want to solve for pressure. That means we need to really divide V to the other side. And again, it ends up in the opposite location. And that gives us P is equal to nRT over V. Putting our numbers in, we get 1.82 moles. We get 0.08206 liters atmosphere Kelvin mole. We get a temperature. Again, we want to make sure we use our Kelvin temperature. And our volume of 5.43 liters. In terms of units, the moles will cancel. The Kelvin will cancel. The liters will cancel. Going to leave us just atmospheres left over, which is good. That's going to give us 1.82 times 0.08206 times 342.5 divided by 5.43. And that's going to give us a pressure of 9.42 atmospheres, which is good because that is a unit of pressure. Any questions on where any of those values came from?
I have a question.
Yeah.
For 342, the last number?
Yeah.
What did you cancel out?
It canceled out the Kelvin.
Oh, okay.
With the gas constant Kelvin, like this Kelvin that's in the gas constant, and the Kelvin from the 342, one's on top and one's on the bottom, they cancel each other out.
And then for the moles, it cancels out between the first one and the one in the fraction?
Exactly. This guy right here. Yeah.
Okay, thank you.
You're welcome. Other questions? Okay, so we're going to stop here today. We're going to talk about a couple